Welcome back. So we talked about minerals. All right. Now let's talk about rocks. They are two different things. Now, the rock cycle is tied into the plate tectonic cycle, which we did learn about back in Unit 2 or so, and how that drives earthquakes and a number of other things. We'll learn more about the plate tectonic cycle interacting with the rock cycle, which is what helps to cause volcanoes and a type of rock called igneous rocks. More on volcanoes in a later unit. But when we're looking at the rock cycle, there are three different types of rocks. There are igneous rocks. Sometimes igneous rocks are created below ground, those we call intrusive, or sometimes igneous rocks are created on the surface, called extrusive. But in any case, we have igneous rocks. They go through this process to then become sedimentary rocks, and then continue along the cycle to become metamorphic rocks. So we'll talk about each three of those things. But the big thing with the rock cycle is it's not just one circle. It's not always igneous, sedimentary, metamorphic. That's how it'll be presented here. That's how you typically learn about it in a geology class, because it makes sense in kind of the story of geology and in how that cycle progresses. But it can really go any way. You can go from igneous rocks to metamorphic rocks to sedimentary rocks, back to metamorphic rocks to igneous rock, to a different type of igneous rock, to a different type of igneous rock, to sedimentary rocks. It just goes all over the place. But for sake of a story, we'll kind of just keep it in that order. We'll first talk about igneous rocks, what those are, how they're created, and also what sort of natural hazards we might encounter these types of rocks at. And then sedimentary rocks, same thing. And then metamorphic rocks, same thing, where we might see these rocks, how they play a part in some natural hazards. So let's continue on. So what is the difference between a rock and a mineral? I had mentioned that those are different things, and they truly are. I mean, not everything hard is considered a rock. I guess you could call them all stones if you wanted, but there is a difference between a mineral and a rock. They are two different things. So when it comes down to it, the definition of a rock is simply a naturally formed, coherent aggregate of minerals, two or more, usually, and possibly some other non-mineral material. So basically a rock is typically, not always, but typically a combination of two or more minerals and maybe some other stuff. Maybe some biologic stuff, maybe some shell fragments, some bones, some twigs, something else. But yeah, at the simplest, a rock is typically two or more minerals. Typically. There's always exceptions to that. Rocks do a great process of recording Earth's history and processes. So when we're looking at different types of rocks, they're formed different ways. So that can inform us what was going on Earth, whether it's just normal Earth stuff or hazard related, based on the types of rocks that we see. So how does minerals kind of play into rocks? So again, minerals, so rocks are a combination of two or more minerals. For instance, if you take the mineral quartz, types of minerals called feldspars, orthoclase, and plagioclase, and then flat micas like muscovite and biotite, when you combine those together, you get a type of igneous rock called granite. That very same granite, if you break it down to create small pieces of sediment, can create sedimentary rock called sandstone. Or if you take that granite, apply some heat and pressure, you can turn it into a metamorphic rock called gneiss. But in any case, all three of these rocks have the same minerals in it, so it's just the arrangement of minerals, how they're arranged and how that arrangement came to be, that will help us define these different types of rocks. Because they're all made from the same stuff. They're all the same thing. But it's just how that stuff was put together, where it was put together, creates these different types of rocks. So let's first get into igneous rocks. So I want you to think about that word igneous, as in ignite, fire. So igneous rocks are born of fire. So these types of rocks form from the cooling and solidification of magma, that's liquid hot rock below surface, or lava, which is the same stuff just on the surface. So when that material cools, whether it's magma or lava, they're both molten melted rock. So when that cools and solidifies, you get an igneous rock. The type of igneous rock form depends on the cooling rate. how fast does this stuff cool? For instance, magma underground cools a lot slower. It's like if you're cooking a pizza in the oven and then you turn the oven off, but you leave the pizza in there. It's still hot in there. It's going to slowly cool down. So you're going to be cooking that pizza still less, but you're still cooking it. Versus if I just took the pizza out and let it cool in the air. Well, same thing with igneous rocks. How that magma cools, which it can be a long time, which can be, in fact, thousands of years, versus if that same molten material erupted onto the surface of the earth as lava and cooled very quickly. So the type of igneous rock depends on how fast or how slow this stuff cools. Sometimes igneous rock have big chunks of visible crystal grains of the different minerals. That typically indicates a rock that cooled very slowly, which indicates a rock that cooled inside the earth. So if I'm now standing on the surface of the earth and I'm holding an igneous rock with big chunks of crystals in it, well, that cooled underground. How is this above ground? What processes or hazards brought this up? Sometimes igneous rocks have vesicles, little holes, air bubbles. That indicates material that had been shot out of the earth. When it happened, there's a lot of gas in there, and as that rock cooled, sometimes immediately as it's flying through the air, it trapped those kind of air bubbles in there. So you see little vesicles, little pockets of air in these rocks, and that indicates, oh, this was kind of shot out of the earth. So it's the ability to read rocks and the story they tell. Again, magma is molten rock below Earth's surface. Lava is molten rock above Earth's surface. So whether magma cools or lava cools, it's all the same stuff. You're just cooling at a different rate, thus creating different igneous rocks. So, for example, intrusive igneous rocks. These form from magma cooled inside the Earth. You get larger crystal grains, like you would see this coarse-grained igneous rock that has something called a phaneritic texture. You can get something called porphyritic texture in it. Maybe it was cooling, this magma was cooling, and then it got pushed up and closer to the surface, so it cooled a lot faster. So you get a mix of big and small crystals, something called a porphyritic texture. Or maybe that molten material was extruded onto the earth, lava, and it cooled very quickly. Then you get a very fine-grained texture called aphanitic texture. You don't see those big crystals because it cooled very slowly. Think about ice. If you take a tray of water and you leave it in the freezer for a day and you pull it out, you'll have big ice cubes. If you leave it in the freezer for only an hour and you pull it out, you'll only have small little chunks. Well, kind of the same thing here. If I'm cooling down for a long time, bigger pieces, bigger crystals. If I'm cooling very slowly, not very much time, only little pieces, littler crystals. And then you have things like pyroclastic or vesicular texture when material is exploded out full of gas. When you're looking at these different things, that can, as kind of a preview, help you infer information about volcanoes, hazards, and disasters depending on the type of igneous rock you're looking at. So, again, what are you looking for if you're trying to identify igneous rocks? A lot of times crystals, whether they're visible or not. These two rocks are made of the exact same stuff. This is granite, this is rhyolite. They're made up of the exact same minerals. Quartz, plagioclase, orthoclase, biotite, muscovite. It's just this one cooled slower, so below ground. So the crystals got bigger. This is lava that extruded at or near the surface, cooled very quickly. So all those minerals only falling into small little pieces. If we looked at this one on the right under a microscope, it actually might look like this. But kind of two different rocks formed two different ways, but still made of the same material. So we're looking for crystals. Another good indication of igneous rocks are vesicles, these little air pockets that we see, tiny little holes created by trapped gas. And we typically only see that in igneous rocks. So that can inform us some materials maybe exploded, shot out of a volcano. So that would indicate, a large eruption. Sometimes another thing we could look for is glassy texture. This is the rock obsidian. It's an igneous rock that cooled so quickly it formed what's known as this amorphous glass. So it's razor sharp glass essentially, if you've ever seen obsidian. As far as natural hazards are concerned, if I'm finding igneous rocks in an area, what does that indicate? Well, a good indication of some type of volcanic rocks could be volcanic eruption. If you're looking at a bunch of volcanic rocks that had air bubbles in it, you're probably in an area that had some sort of explosive volcanic eruption. So you could either look for vesicles or igneous rocks with the tiny crystals, the aphanetic texture, meaning that lava extruded out to the surface and cooled very quickly. So there was some sort of lava flow eruption. Or even glassy type igneous rocks like obsidian cooled so fast it created this kind of glass. But again, there are some igneous rocks that cool below ground, kind of these intrusive igneous rocks. So what do they indicate? If I'm out hiking around, let's say, the White Tank Mountains or the Estrella Mountains, I'm going to come across a lot of granite. Well, granite is a bigger, chunkier grained igneous rock, meaning that cooled below ground. Well, if that cooled below ground, how am I now walking on it? How am I now hiking through this big granite mountain? Well, that can indicate some sort of tectonic uplift. If I'm looking at large, visible, crystalled igneous rocks, if I know what at least is igneous rock, and it has bigger crystals, how am I walking it? There must have been some tectonic uplift. Think back to plate tectonics, how that moves things around, basin and range formation. It tells a story. Rocks can tell a story. That's why I said that at the beginning of this section. So here's a bunch of different igneous rocks. So you can see the ones with the different crystals. They're visible. You can see the black and the white and the pink. Over here it's more gray, black, and white, gray, and black. So you can see the visible crystals in these things. Some of them, again, you see these air holes as well. So these can be great indications of igneous rocks. So what we're going to do, we'll go ahead and because this is kind of a bigger section, we're going to go ahead and pause here for just now. And when we come back, we'll talk about sedimentary rocks and metamorphic rocks, and that will actually wrap up this unit. So I will see you back here in just a second.